Hello, this is Dr. Brown. This is going to be section 5.2 in our textbook, and we're going to be talking about properties of rational functions. These are three of the topics we're going to look into. First of all, we're going to find the domain of a rational function, that is, all the values of x that you can substitute in to the equation. Then we're going to look at what we call the vertical asymptotes of a rational function, and then look into what we call the horizontal and in some cases oblique asymptotes of a rational function. Now, you probably will recall that a rational function is a ratio of two functions, p of x and q of x, where p of x and q of x are polynomials. And one of the things you ought to take note of is that the domain is determined by q of x, the denominator. And basically you want to look and see whether q of x has any zeros. If it's zero, then those zeros are not in the domain. R of x can have zeros, and there the only way you can have zeros is for p of x, the numerator, to equal 0. Don't ever set the denominator q of x equal to 0 to try to determine zeros of the function. So now let's find the domain of a rational function. Some examples. Let's look at 2x squared minus 4 over x plus 5. Notice that the x plus 5, the denominator, equals 0, then x would equal minus 5. So minus 5 is not in the domain. So the way you would write it is x for x not equal to minus 5. This is a formal way you would write it. Looking at example B, r of x equal 1 over x squared minus 4, you would quickly factor the denominator into x plus 2 and x minus 2, and obviously you would now write the domain as x not equal to minus 2, and x not equal to 2. This particular one, notice that x squared plus 1 equals 0 has no real zeros. And so the domain is all real numbers. Finally, the last example, r of x equal x squared minus 1 over x minus 1. X minus 1 equals 0. X equal 1. So the domain is x such that x is not equal to 1. Now let's look at graphing a very simple rational function, 1 over x squared, and take a look at some of the values of x. In particular, as x gets close to 0, notice x cannot be 0. If you plot the function, in fact, let's go ahead and do it on our calculator. Y equal 1 divided by x squared. Let's go ahead and just zoom to the standard window 6. And somehow the x squared did not take here, so let's try that again. 1 divided by x hit squared. Now it should work. Graph it. And there we have, see what we would call the vertical asymptotes. Notice that as x gets closer to 0, the function goes to plus infinity. And over here in the table, as you substitute various numbers for x, if you put in 1/2, you get 4. You put in 1 over 100, which is getting closer to 0, you get 10,000. 1 over 10,000, you get 100 million. And notice, so therefore, that as x gets closer and closer to the y-axis, y approaches what we would call infinity. Notice the other thing, this would be what we will call a vertical asymptote. Now notice as x gets larger and larger, and you're dividing 1 by a larger and larger number, x squared, that the value of the function gets very, very small. In other words, if you put in like 10,000, you get 1 over 100 million, which is very small. These would be called horizontal asymptotes. That is the number that the function approaches as x goes to either plus infinity or minus infinity. Now let's graph the function 1 over x minus 2 squared plus 1. And let's put this in our calculator, and we should get the same graph you're seeing here. I recommend that you graph all these yourself as we go along. First, we'll put in 1 plus 1 divided by parentheses x minus 2 quantity squared, and we'll go ahead and graph it. It'll zoom to the standard window. We could zoom in, and it would look exactly like you see here on the slide. Notice that now x equal 2 x equal 2 is a vertical asymptote. notice as x gets very large, that y gets closer and closer to 1. Now, these tables are showing various values of the function r of x as x approaches or equals certain numbers. Notice at x equal 10, y is pretty close to 1, 1.0156. As x goes to 10,000, you put it in your calculator and you get a number that's even closer to 1. If you put in minus 10,000, you get a number that's very close to 1. And notice as x gets close to 2, the function gets larger and larger. If x is not close to 2, like at 1.5, the value of the function is 5. But very quickly, as you get to 1.9, which is close to 2, the function is already at 101. And finally, as you get to 1.9999, you're at 100,000,001. The same is true if you get close to 2 from the positive side of 2. If you get to 2.0001, you again, the value of x is 100,000,001. So this just illustrates what happens when a function has an asymptote. Now here's a definition. By the way, there is some notation here. If I write x with an arrow to the right with an infinity, that says x is approaching infinity, or x approaches minus infinity. So here is the definition. If as x approaches minus infinity or plus infinity, if the value of Rx approaches some fixed number L, and L is sometimes called a limit, and it's also called a horizontal asymptote of the graph of R. Also, if x approaches some number c, for example 2 on the previous graph, if the value of r of x approaches infinity, then that is r of x approaches minus infinity or plus infinity, then the line x is called a vertical asymptote of the graph of R. Now here are some examples of asymptotes. Here is one in which as x approaches infinity, the graph gets closer and closer to the number y equal L. That's behavior on the right. Now for behavior on the left, suppose a graph as x gets closer to minus infinity, it goes to closer and closer to the value L. That's also called a horizontal asymptote. Now, vertical asymptotes, if x is getting closer and closer to c, you can see that either from the left or the right, the function is getting closer and closer to plus infinity. You could also have other variations in which from one side approaching, say, c, you're going to plus infinity. On the other side, you're going to negative infinity. And you'll easily see these as you graph various functions. Now there is another kind of asymptote called an oblique asymptote. Sometimes we call it a slant asymptote. And in this particular case, as x goes to infinity, the function does not approach a constant value. It just simply gets closer and closer to a straight line. In fact, this straight line could be y equal mx plus b, which you notice is the general equation for a straight line. And we will see a little bit later that to determine what the oblique asymptote is, you use long division, which is one thing you're going to need to learn very quickly. Now let's find the vertical asymptotes of a rational function. To find the vertical asymptotes, you get p of x over q of x and put it in lowest terms. And that's an important thing because if you get it in its lowest terms, in other words, cancel all common factors of p of x and q of x, then the zeros of q of x will be the vertical asymptotes. Now, just as a quick example, if p of x were like x squared plus 2 over x minus 1 x plus 2, notice that this is in its lowest terms, so x equal 1 and x equal plus 2, or I'm sorry, minus 2, would be vertical asymptotes. On the other hand, if you had factored p of x over q of x, and you got x minus 1, x plus 2 over x minus 3 times x minus 1. Notice you can cancel the x minus 1 in the denominator and numerator. So the only vertical asymptote would be x equal 3. X equal 1 is not. It would be, however, what we call a hole in the graph. So let's find the vertical asymptotes of these four functions. This particular function is in its lowest terms. In other words, you can't cancel any terms in the denominator and numerator. And so set the denominator equal to 0, and we get x equal 1 is a vertical asymptote. pretty straightforward. Here, the second example, you can factor this into x minus 2, x plus 2. Notice this is in lowest terms. The x minus 2 or x plus 2 cannot be canceled in the numerator because they aren't there. So we would say x equal minus 2 and x equal plus 2 are vertical asymptotes. The third one here, it's also in lowest terms. And notice x squared plus 1 is always positive. It will never be 0 because x squared plus 1 equals 0 gives you x squared equal minus 1. Notice that has no real solutions. We will learn later on that x equal I and x equal minus I, these are imaginary numbers, are zeros, but they're not real. So there are no vertical asymptotes. For the third one, for the fourth one, we need to factor the numerator and factor the denominator. You're going to have to remember how to factor in this course. And notice, in this particular case, both the numerator and denominator have the common factor x minus 3. So x equal 3 is not in the domain of this function, but it is not a vertical asymptote. The only vertical asymptote is x equal minus 7. In fact, I would like to graph this function. Just to indicate, let's now use parentheses, x squared minus 9 divided by x squared plus 4x minus 21. It's important to use parentheses and use I'm curious here. Okay, looks like it got entered correctly. And then I'm going to zoom to the standard window. And notice the only vertical asymptote is at x equal minus 7 over here. Notice that as x goes to plus infinity, the graph is flattening out, which indicates a horizontal asymptote, and looks like it's approaching 1. And we will show a quick way of calculating horizontal asymptotes in just a second. Now, vertical asymptotes can have various kinds of flavors, or what we might call multiplicity. Here is an illustration where as x approaches 2, y approaches minus infinity on the left, that means as x is approaching 2, we put a minus there at the top, which means it's approaching 2 from the left. Now, x approaches 2 from the right, it goes to plus infinity. Notice it could also be flipped and be plus infinity from the left and minus infinity from the right. Sometimes it could be an even function with respect to the vertical asymptote x equal 2 and go to plus infinity from both sides, or if it's flipped, minus infinity from both sides. So now let's find the horizontal or oblique asymptote of a rational function. I'm going to go through this and then maybe even show you a faster way. If you write down the rational function, where n is the degree of the numerator and m is the degree of the denominator, if n is less than m, if n is less than m, then y equals 0 is a horizontal asymptote. That basically means that the denominator, because m is more than n, is overpowering the numerator, which gets bigger and bigger as x goes to infinity, and so it goes to 0. If n equals m, then you will find that all you need to do is take the ratio of a sub n over b sub m, and that will be the horizontal asymptote. If n is just one more than m, then we have what we call an oblique asymptote, and we'll have to use long division to find out what it is. And if n is more than m plus 2, then the degree of the numerator, if it's 2 or more greater than the degree of the denominator, then there are no horizontal or oblique asymptotes. Now, a really quick way to determine asymptotes as x approaches infinity or minus infinity is to write down the rational function. And you will recall that for a polynomial, as x gets large, it's dominated by the terms with the highest coefficients. So write down the ratio of terms of highest degree, and then take the limit of h of x as x approach infinity or minus infinity. Let's just do an example. Suppose r of x equals 3x cubed plus 2x minus 5 over x cubed minus 2x plus 5. And you want to find the horizontal asymptote. Just write down the dominant terms, cancel out these x cubes, and that equals 3, so the horizontal asymptote is 3. It's the same thing the previous slide showed, that you just look at a sub n over b sub m. On the other hand, the other hand, if r of x was equal to 5x to the fifth minus 2x over x cubed plus 8x minus 10, if you write down the dominant terms, you get 5x squared. So if x goes to infinity, this goes to infinity, so there's no vertical asymptote. One more example. If r of x were equal to 3x squared minus 2x plus 4, and the denominator was equal to 5x cubed plus 12x squared, we could write the dominant terms as 3x squared over 5x cubed equals 3 over 5x. Now, as x goes to infinity, r goes to 0, because you take any number 3 and divide by a large number, 5x, it will always go to 0. So now, in this particular case, we're going to find a horizontal or oblique asymptote. So we want to find the horizontal or oblique asymptote of this function. Notice that the degree of the numerator is 1 more than the degree of the denominator. Therefore, it's going to have an oblique asymptote, and we're going to use long division. Now, you need to practice doing long division, and it's like it says, you take the numerator, which is x cubed minus x squared plus 1, and write down you're taking the denominator, which is x cubed minus x squared plus 1, and dividing it into the numerator, which is 3x to the fourth minus x squared. And you need to leave a place for x cubed. So you write it like this, and then take x cubed and divide it into 3x to the fourth, and you get 3x. Then multiply 3x times your x cubed minus x squared plus 1, and you get 3x to the fourth minus 3x squared plus 3x. Now subtract this line from this line. 3x to the fourth minus 3x to the fourth is 0. 0 minus 3x cubed is 3x cubed. 0 from minus x squared leaves minus x squared. And 3x from 0 leaves minus 3x. So now we'll take 3x cubed divided by x cubed again and get plus 3. Now multiply 3 times the divisor, and you get 3x cubed minus 3x squared plus 3. Subtract again, and you get 2x squared minus 3x minus 3. And this is called the remainder. So h of x can be written as 3x plus 3 plus the remainder And from this, the linear terms will be what we call the oblique asymptote. So the oblique asymptote is going to be y equal 3x plus 3. I recommend you practice this in your homework. Now, g of x equal 2x to the fifth minus 3x cubed plus 2 over x cubed minus 1. Notice a real quick way to look at this. G of x is approximately equal to the dominant terms. And notice that this goes to infinity as x goes to infinity, so there's no horizontal asymptote. And this explanation shows exactly what we just showed. Well, that is the lesson for today.